So this is the final video of our understanding the derivative videos. And if you're watching this one, I'm assuming you've watched the previous ones. So the first one was all about using an analogy. So thinking about our derivative as um, as a spaceship and thinking about the top of the spaceship and how high that is above the back of the spaceship. We talked about launching it from different points. In video 2, we applied this launching the spaceship idea to a quadratic, to a function that looked like this, to a graph that looked like this. We applied this concept to say, well, if we want the derivative here, all we have to do is launch a spaceship from there and look at how high above the front is from the back. We want the derivative at 0.59, 5 is x, 9 is y. All we have to do is launch a spaceship from 0.59 and keep it in line perfectly with the graph and see how far above the front is than the back to find the derivative. If we want it from 10, just launch it from 10, 12 in line. And then in video 3, we answered, we explored how cool it would be if we could work out how the spaceship was pointing without drawing the spaceship. And we worked out that in fact you could use the derivative equation. And the derivative equation tells us how the spaceship is pointing at any x value. And so we took the x value 0 and put that into the derivative equation. This was the original equation. We substituted in 0 and we found that the derivative equation gave us the number 2, which was what we found out when we drew the spaceship. Then we looked at the x value of 5 and we got out 1, which was again what we had when we drew the spaceship. The spaceship was pointing 1, and then when x equals 10, and again we got 0. So we had spaceship's pointing 2, the front's 2 above the back, or 2 above the dy over dx equaled 2 here. Then we looked at this one and it was 1, and this one and it equaled 0. But now this final video is relating it all to this concept of rate of change. Because you may have heard people say before, derivative is all about the rate of change. So, derivative and rate of change. Well, turns out this is actually the easiest spot of this, right? Because all we have to think about is what's the rate of change of the spaceship's height. So if we launch our spaceship at different angles, in which situation is the spaceship going to get to space the fastest? If we launch our spaceship straight up, like that, our spaceship's going to get to space super fast, isn't it? If we're going to launch our spaceship like this, it's going to take a bit longer because it's going to go on an angle to get to space. If we launch our spaceship on this angle, it's going to take even longer than both these situations. And if we launch our spaceship from this angle, it's never going to get to space. It's just going to keep on going horizontally around the world. So it's just going to always go flat in line with the land. So we can think of the derivative as a way of rating how fast the spaceship is going up. Derivative and rate of change. So derivative equals a way to rate how fast the spaceship is going up. Another thing we could talk about is the rate of change of height of the spaceship. So if we've got any function, if we've got a function that, we might have something that looks like this. It might look like this. And we say, what's the derivative at this point? Well, all we have to ask now is, well, how fast is the spaceship going up? Well, the spaceship isn't going up at all. It's just going horizontally, isn't it? So if we rate how fast the spaceship is going up, well, it would just be 0. Right? If we rate how fast the spaceship's going up here, well, we might have 1 and 1. And if we rated how fast the spaceship was going down up here, well, it's not going up. It's actually at all. It's actually going down. This might be 1 and this might be 1. So dy on dx. Well, the spaceship's front is actually beneath the back, so we have to have a negative. And then this one's still just a 1. So that might be -1. The spaceship's, if we were rating how fast it's going up, well, it's got to be a negative rating because it's actually going down. So when we're linking the derivative to the rate of change, and we're thinking of it as the rate of change of height of this spaceship. And ultimately, the derivative is just a way to rate how fast this spaceship is going up. Now, this might seem like a weird way to think of a mathematical concept, but it actually has parallels in reality. The derivative relates distance to velocity, and it relates velocity to acceleration. And so we could actually do a mathematically and physically accurate example of using a spaceship and using these kinds of graphs and these techniques. But what we've also done is we've used an analogy. We've taken something that we already know about, which is a spaceship, and we've linked it in an abstract way, which is using a mnemonic, to this concept of the derivative, which is originally something really hard to get our head around. So what have we done? Well, hopefully we've given ourselves a better understanding of the derivative as a way to rate how fast the spaceship is going up. And hopefully it's pretty clear now that if you've got a quadratic and you want to know what the derivative is at the highest point, then it's just going to be 0. So that's one of the key take-homes. If we're going to want to know what the derivative is at this point, well, it's going to have to be positive. If we want to know what the derivative is at this point, well, it's going to have to be negative because the spaceship's going down. So this is one example of how we can use an analogy and a mnemonic to better understand a really abstract and difficult concept like the derivative.